Welcome to today's webinar. The topic today is stress analysis of surfaces and members in RFEM 6 and RStab 9. My name is Andreas Hörold. I will be the moderator today. A short introduction. I've been working for 12 years for the company Dlubal Software. I'm responsible for marketing and PR. For instance, the Dlubal website, German and English webinars, customer projects, and so on. I will also answer your questions together with Frank, and Andreas Niemeyer will be the presenter today, but they can introduce themselves.
Okay, my name is Frank Vorstich. I'm responsible for quality management, and today I will answer your questions.
Hi, I'm Andreas Niemeyer. I'm working for Dlubal now up to 16 years now. I'm responsible here for the product engineering. I take care about all wishes, about all wished features from you. And today I present this webinar.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. For those people or attendees that attend the webinar the first time, you can ask questions via the control panel. You can show or hide it with that arrow here and then enter a question here, and Frank and me will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's all from my side. I hand over the screen to Andreas. Andreas, it's your turn.
Okay. Thank you, Andreas. Then I overtake with the topic stress analysis of surfaces and members in RFEM 6. And my example, what I want to present today, I collected from various customer cases, and today I want to show you how you can model such a vessel standing on a steel rack. With an opening, with a manhole opening, and how to say, unbolted head closing on right and left side. For presenting this, I defined 4 main points. What is important for me to show you, I show you how this structure could be modeled and designed according to stresses, how you can do a strain check if you use a nonlinear material, and how you can reduce your report, your documentation by using member representatives, and finally how you can set up a documentation for your clients. And now this is the point where we can jump into the live demo. So I change now to RFEM 6 and let's open a new model to define this vessel construction. Let's give here a name, for example BU. We use here a 3D environment, and for this task what we have to perform here, I define my tasks here a nonlinear material behavior to consider later a nonlinear material, and I activate here for the design checks a stress strain analysis add-on. Further, we have to define here in these settings the upward direction for the global z-axis. And now we can jump into the program and get an empty environment. Here you see our graphic environment, on the left side the navigator, on the bottom the tables which output the input and result data. For starting modeling such a vessel, we have to think how we want to set it up, and I mentioned this vessel should have a vaulted head on the right and left side, and this structure, maybe I jump back to my PowerPoint here, bases on such a geometry what is defined via the outer diameter, and here on radius 1 for the calotte, and with radius 2 for the brim, and this construction could be performed in RFEM with arcs. So if you want to model such a type, you can place your grids and use here a line type arc. So for example, here we can create a new arc with nodes, and you can pick such arcs into the program by giving 3 nodes or later a radius. But this is pretty exhausting for such a type or a construction, because we have to find a situation where both radius running in one point, so between calotte and brim. So I decided to show you today the construction of this vaulted head via a script. And for this, I added here in our script manager below examples a vaulted head script tool, which allows us by double-clicking run a few commands in the program behind. Before these commands will run, the program asked me about outer diameter, the thickness of the vaulted head, and the shape. I defined this tool with 2 options, with 2 shape options, one with torus-spherical head, or the second with a round head, the simple solution. And if I run this solution, you will see the program generates for you such a construction. Of course, I just mentioned we have this more complex solution. I delete this again and run this tool again and define directly my dimensions. So in my case, I have a 2.3 meter radius, here 29 millimeter thickness, and I want this shape torus-spherical. And if I run this tool, we get here from our program this geometry with these 2 arcs, with this, let's say, defined radiuses behind, and I can use this structure now for further modeling. Now, this is looking to you, I suppose, really like a black box, and I don't want this. Therefore, let's take a look behind this. And I open this tool here, and we see it's a simple, let's say, script file. We can open it with any editor, and if we take a look in the content, you see in the begin I have some variables, so radiuses, this big one, the small one, and so on, so material definition, thickness definitions, and finally we come to the modeling, where we can decide for shape 1 some actions or for shape 2 some actions. And if we take a closer look, what happens if we select, for example, shape 1, the program is generating a few nodes, node 1, 3, 4, 5, 6, then it generates an arc line between the nodes, here between 1 and 3, a second arc line between 3 and 5, and finally it creates a surface around these arc lines. So it's no rocket science behind. You see this small script is almost 100 lines. It could be done by yourself. I only want to give you these options and inspire you what you can do. And it's easy to create in RFEM such small tools by yourself, not only geometries and also loads and loading and combination, whatever you want. You have contact to all options in the program and to generate such functions. And we use today this vaulted head script. So Now the most complex geometry is in the program, and we have to combine it to create a vessel. And for this I select these two surfaces and rotate it about the y-axis. So here rotate, let's say minus 90 degree about y-axis, and the rotation point is okay, the origin. Now we can move it maybe a little bit into the left side, that the origin and the mirror point of the full structure is in the middle. So I move this surfaces minus 1.710 meter. So because we have to define now more millimeter dimensions, I change this unit to millimeters here, and you see the program is recalculating this input directly to millimeters, and after confirmation this part is offsetted. Now we can take this part again and mirror it on the right side because it's similar. So we use the mirror command about YC. So we create a copy. Mirror plane is YC and containing the origin. And with confirmation you get now two parts, so the two ends of this cylinder in the environment. Now we have to close it with the cylinder surface. This is pretty easy. We can connect these upper two nodes, and we create two parts for this cylinder. So I select this line, rotate it by doing a copy 2 times with 180 degrees about the y-axis, and to get directly surfaces I use a step link functions. And a step link function means that I can create between the origin element, what I copy or rotate, and the new target element a surface. So I pick here this function where I say please create a surface in between, and here I open the function which surface properties this target surface should get. I say okay, stiffness type is fine, but thickness should be not taken from the voided head, then it should be taken from a new setting, and I define here a new thickness setting cylinder, and define here for example 26 millimeters. Now we have done all settings in this dialog, and we confirm here that this rotation should create arc lines, and this okay. Oops, again I missed something, I suppose. Rotate 2 times 180 x-axis, and now step links and template, and now it should work. Yes. So this is the job to get such a vessel from metal sheets in the program. As next I would control the material. Here we get the standard material S235. In my case I have a stainless steel, so I modify the thickness definitions of the surfaces, what is similar to a cross-section of a member. I select both and go into the library, select here a stainless steel and search it with a key number, for example here 1.4318 from this EN 188 with this P solution. And if we check the properties of this material, we see, okay, we have here stiffness relevant data, and we have here yield strength of 330 Newton per square millimeters. Now, after using this setting in the dialogues, the program is assigning this steel to the surfaces. You see it by another color here. In the next part of this presentation, we have to take care, or to take care how people can maintain this vessel, how we can come into this vessel, and we are forced to create a manhole in between. The manhole should be placed in the middle here and should have a elliptical shape. The elliptical shape is projected in the plane XC and is cutted through this curved surface here. And the question up here is how we can create such a opening in RFEM. And here I want to show you two new commands. So let's make it visible. Let's use this wireframe model. Let's use this grid plane behind. For this, for getting or defining a right size of this manhole, I'm changing the grid distances. So I open the settings here and say, okay, the width of the manhole is 300 millimeters, so I use a half of it, 150, and the height of the manhole is 400 millimeters, so let's use a half of it, 200. Now we have points here which we can use for picking the geometry. The elliptical function is not should not be constructed from straight lines, and we support you here with some special line functions with elliptical functions where we can use, for example, this arc function. And you see this elliptical arc is defined by 3 nodes or points, P1, P2 and P3. So let's pick it on our prepared working plane, P2, and finally the second node here in X direction, and with confirmation we get a half of such a elliptical shape. Now let's mirror this shape on the another side. So use a mirror command. Mirror plane is YC. A copy. Mirror point is the origin. So everything is fine, and we get here this, let's say, elliptical shape for this manhole in the projection plane XC. Now we can use this geometry for cutting out the hole of the curved plane, but before I want to think about when we cut out the hole of this vessel. We have a hole here and it's pretty slender, so we want to stiffen it. So we want to create a stiffener around the hole, and the stiffener should have a height of 150 millimeters and a thickness of 20 millimeters. So I use these 2 lines to create this stiffener first. For this I copy these 2 lines one time in Y direction with 150 millimeters, with using step links by saying using a specific thickness or surface property setting. So I define here a new thickness setting manhole, for example. So with the material of the stainless steel material, and the thickness is as planned 20 millimeters. Now with confirmation, we get now the stiffener of this manhole in projection, and now we can use this surface part what is lying inside the vessel. If you use this transparent view, you see it's inside the vessel. We move it outside to the border of the vessel. For this, I use my working plane, create here a line from, let's say, the center of the elliptical shape to my side here. This line is now cutting the cylinder. I use here the connect function to find an intersection point, and you see the program is creating exactly on the intersection between surface and line a node. I can delete the rest. And now let's move this stiffener from the center to this node. For this I define a center first between the first center and the second center. Applying, we get now a node here in the middle, and now we can select both and draw this model to this intersection point what we prepared. And now this shape, let's check it here from this view, is exactly in the middle of this outer hull of this vessel. Of course, if we check it now, we see they don't know from each other. So I cannot look through. This means when I select only this part here, we will see, okay, it's not visible. To get a hole here inside, we select all three surface parts. Go into the properties here for surfaces, and you see you get here a few new commands. And for this, because we expect the opening, we use divide by intersection and create opening. With using this command, you see now we can look through, and the program created us a three-dimensional opening on the hull of the cylinder and cut it this elliptical shape into several parts which I can open and can assign new properties, thickness, mesh refinement, whatever. It got a new type, trimmed. So it's a new surface what you can use for all other things. You can copy, drag, whatever, but it holds the shape from the intersection. What is a really powerful tool, I would say. So this is the first part. Now we are finished with modeling the vessel, with having this manhole, and we can finalize it now by creating this rack for this construction. The rack is finally here placed in this plane here, and for this I use a rectangle surface, stiffness type without thickness, because I use it only to find the right geometry. I use my grid points and pick here a plane. Now if we watch this in isometric view, you see this is in the middle, so let's move it to right and left side. So let's use copy move command without copy and move this surface 1500 millimeters into the right side. Okay, and now we can copy this surface one time with minus 3000 millimeters into the left side. Now these two red planes are now the placeholder for our rack construction. Before we start with rack construction, we intersect these red planes with the cylinder by using our command divide by intersection. What happens? After intersection, the program don't create the opening because there is no opening. Yeah, I don't have a closed line circuit, but we get here surfaces intersected in an outer and let's say in a inner part. We can delete the inner parts, and we can also delete the outer parts, because we are only interested in the bottom line and in the intersection line. And this is now the basis for the rack. So we want to connect here a channel section to the cylinder. But before we go ahead with this channel section, because here the orientation of surface for the eccentricities is important, we start orienting the eccentricities or the directions of the surfaces. For this, I mesh the construction. For testing and for getting a quick calculation, at first with 50 millimeters. For the final design check, I would say we have to use a finer mesh, but for setting up this model, 50 millimeters is okay. And we create a mesh. Generate mesh. And you see, okay, for the global structure, the mesh looks fine. Even this hole is considered, but we are interested in direction and orientation, so we check it here with mesh axis directions, and you see now a forest of coordinate systems. But we see generally all blue z-axis are perpendicular to plane and showing outwards. Only the right side, and even here they are wrong. So let's hide it and rotate it, and let's say here surface reverse axis system. The same here for these two surfaces. Right click axis system, and to finally later close the vessel, I apply here a rigid plane to close this vessel. So I pick this line now. Now let's check it again with this axis system. And you will see all axis systems now showing outside. Even for this manhole construction, we can see that even here the planes are showing out, the directions are showing outside. So everything is fine, and we can go ahead by assigning members to the structure. So for this we select these two arc lines, go into the properties, edit lines, and select here, please assign a member. The member is clear. Now we can say which cross section the member should have. Here we use the library and select here channel section, and for example here the channel U200 from S235, and we see, okay, y-axis is running in right direction, and we want to weld the back to the cylinder. Yeah. So let's check this. Let's rotate it by 90 degrees, and to have it eccentric, because the program will place it always in the center, we have to move it a little bit outside the cylinder, so we use the eccentricity. For the eccentricity we say, please make it eccentric to the y-axis on the back wall, so on this side, and place it on the top, on the outer side of the surface. On a surface we select here this cylinder surface and say on the positive side, so here. Now we define both settings on right and left side of member, and with confirmation program wants to delete mesh, and you see we have now here a little offset, and if we check it in rendering, you see now we have connected this channel section to the cylinder on the outer side. Yeah. So far everything fine. In the next instance we have to connect this line with a member, so I do almost the same, but without eccentricity. I write here minus 90 degree, the same section, and now we have also this bottom member. To get a good overview in the wireframe model, I only can recommend, because I don't like it to change continuously between these two views, I use here always these member outlines, and you see here exactly how the cross-section is oriented. In the next, we have to connect the bottom member with the arc member. For this I use also a member with a hollow section, rectangular hollow section. The size should be something with 180, maybe with 60 millimeters. And you see, when I use this keyword search, the programs give me all possible solutions with considering the filter here, and I select here this cross section, and finally I can here connect the line. So I did something wrong. Let's move it here. The same property. Okay, now, yeah, I forgot something. So I can finalize this member here, but I want to connect now this node with the middle point of this arc, but I have no node, so I have to prepare it. So I select these three members, say divide member, intermediate nodes with one center node without dividing it. So this is important for me, that I get here a node and here a node, but it remains as one member. It's interesting for later design. And now we can see if we place these members, it's an easy game. So we can connect this node with this node again with this center node, also here, and the last one here. So finally it looks like this, and if we check this, let's say, orientation of the cross section, you see it's rotated wrong. So let's open this cross section, or select it by selecting this line. Right click, members, edit, section, and rotate it, maybe by a quarter. And now if you use this view, you see so far it looking like expected. And we can use this rack construction by selecting maybe this S235. You use copy command, copy one time from this node to this node, confirm, and we get this rack on the another side. So far, quite easy. The model itself is now finished, and we can start defining boundary conditions. Boundary conditions are nodal supports and loads. So let's start at first with nodal supports. Let's support this structure statically determined. So I use here type for nodes. And you see there are some predefined settings what are not fit, because I think we cannot estimate what you want to do, but we can change it easily. So let's define the fixed point in the center here. And this point should be fixed in X, Y, Z, no rotation. Now the next 2 points should be this right and left point here, and here let's say y-axis is free, the other two are fixed and no rotation fixing. And next is the center node on the other side. So here we have open direction in y and no rotation. And now we can finalize it by defining the two remaining nodes, and here we have no fixation in X and Y, only vertical with no rotation, and the remaining setting we can delete. So you see, with this table input it's quite comfortable to define such complex support conditions in a few seconds. So use it for your advantage. No? So next point, we can start modeling the load cases, and here I prepared to show you 3 load cases. For this I open the table load cases and combinations. You see the program directly define the self-weight load case because it's pretty common, and I would say, or I recommend always to run self-weight load case, and if this self-weight load case is working, so here the program notifies one node is on the same, as we have 2 nodes on the same place, we can maybe here cancel the calculation and open here model check function, identical node, and you see, okay, here we have identical nodes, we can unite it here, and now it should be fixed. And now let's run self-weight load case because it's one of the best plausibility checks. So if this load case is running, you know meshing is possible, you know you have supported everything, and if the deflection is also in a range what is expected, then you see also your loads are fine. But anyway, when you do some load case calculations, I recommend also to check some result plausibility. So for me, it's always important to check the sum of support forces, and you see for the self-weight we have only a vertical force in sum in loads, and support forces are similar. So everything is looking fine so far, and to see about deflection is also fine. It's going downwards, and for stresses to have a feeling if the sizes of cross sections and surface thickness is fine. We take a look on equivalent mesostress of members. You see we have here about, let's say, 6.5, and for surfaces equivalent stress mesos, you see for surfaces we have about 7. So everything in the range. So I would check this load case and want to go to the next. The next load case is internal pressure load case. So we can define here load case 2 with internal pressure. I would say let's use here the category permanent imposed. We have no self-weight defined here, and now we can specify the internal pressure by a surface load. We use here force with local direction in C, what is always perpendicular to the surface, and we know now the surface as the axis C is going outside. We checked it before, so we can write the load positive, and maybe we will have to define 10 bar, but the unit here is something different. You can write the unit directly here, and the program is recalculating it into this unit. So it's also an easy game for you. If this unit inputs don't fit, write it in the unit you need it. And now selecting the surfaces, and even here, let's say the outer ring and the coverage in front. And with confirmation you get now really scaring load symbol, but I would check it a little bit different. So if we run now the calculation of this load case, you will realize that let's say the deflection is fine so far, the vessel is going bigger, and for the stresses we have here 40 for the members and 120 for the surfaces. When you see the red color here in the brim, what is obvious because it induces bending. And what is quite interesting, sum of loads is 0 because we have only internal pressures. There is no external force what should support this structure. So far the result is fine, and if you check distribution of loads, you will see the applied load here in perpendicular direction is homogeneous above the full surface. We have here this 10 bar, so everything is fine so far. Now let's finalize the last load case. Here we define a filling load case. It's almost similar to the internal pressure, where we can use the surface load. We only change here to linear in Z with a local load in local C, and defining here the top point is 0 and the bottom point is 23 kilonewton per square meter for this fluid what we simulate inside the vessel, and the top point 0 and bottom is defined by 2 nodes. So for example, top is here, bottom is here. Now with defining the surfaces again, it should work and output us corresponding forces. You see here this is distribution of load. It's running from 0 to the biggest force here on the bottom. It's stress Newton per square millimeter. Yeah. Then we get only a weight in Z directions, 165, what is also obvious. And for the surface result and member result, you receive here 15 Newton per square millimeters. Yes. So now we have defined 3 load cases, and you see every load case gives different stresses on members and surfaces and different stress components, and you have the task to check it. And to check it, you have to bring in a safety level, so you need some partial safety factors, and here you can use the combination. You see the program offers here a standard combination according Eurocode or any other standards, and if you say, okay, this scheme is not okay for me, I recommend to use this combination without, maybe without, or to use it without. Then you can define combinations by yourself, so with surf weight, and internal pressure, and so on, like you wish. No? Or you use a automatism behind, what means you activate this combination without, and define your design situations, what is interesting for the final check. We say we want to check only ultimate limit state, for example, for the stress analysis, and that the program knows what should be combined. You have here a wizard setting, and the wizard setting is here what allows us to use here user-defined combinations. And if you check this, you're forced to define action combinations, and here you can say first action is, for example, only permanent. The second action is permanent and permanent imposed. And by using these 2 settings, the program is creating from your load cases automatically combined system where it checks maybe surf weight, internal pressure, with filling, only filling. If you say now, oh, I need safety factors, no worry, you can change here to 1.35 or whatever, which factor you need, and here to 35, and here, for example, to 1.5. And if you check it, you get these factors inside your combination product. So it's easy. You see now it's according second order. If this is not wished, give this wizard the setting, please do it according linear theory, and the program is updating it to linear theory. So this is a pretty good tool to create the combinations, and these combinations will be used now in the stress analysis, because we have here design situations. This design situation 1, what is connected to this versus check is given. So if you remove this check, apply, you see it will be removed. If you check it, apply, it will be checked. No? And if we run the stress check, you will see the program is calculating the internal forces for CO1 to 4 and feeding all stresses into the stress add-on. And what happens now? Now we get a colorful picture, what is nice, but let's check results in detail. And you see you have now here stress analysis. Behind is the static, what we just checked. And you get now here some stresses for members. You see here positive, negative stresses for sigma x, shear stresses, or maybe equivalent stress. And then it compares these components to the limit stress by a ratio. The same for the surfaces. Sigma 1, 2, on positive side, negative side, equivalent stress, and compare it to a ratio. So ratios may be up to existing compared to the allowed stress. The question is now which stress component I should compare. And now let's start with members. If you check the stress strain input, you will see we have here our member configurations. And you see the program shows us an endless table of stress components, what he can calculate, only normal axis force, compression force, tension force, whatever. As engineer or as designer, I'm interested now in Mises equivalent stress. And in the second column, the program asks me, what is my limit stress? You can select here no limit stress, normal stress, shear stress, equivalent stress, or user-defined. It depends. Let's use now a user-defined to show you the options what the program have. I use, for example, here 85% of the yield limit stress, so 280, for example. And the same could be done for surfaces. It's almost similar. So if we open this setting, you see the same, only for surfaces. Let's check here also only Mises stress with a user-defined stress to be similar to 80. And if we run now stress strain analysis again, you see no internal forces have to be calculated because they are already here. And now this tree is smaller. We only calculate equivalent Mises stress. It's now 64, the biggest one, of CO1 to 4. And the biggest stress compared to the limit stress 280 is maybe results to in the members to 23%, in the surface to 66%. No? So far. No? Now we come up and say, is this the limit of the program? Stress strain analysis, do we have more options? And I would say you have now option to design members, surfaces, of course also solids. But if I watch this model, I would say line welds would be also interesting. So I can also define a line weld here. If I jump back to my basic input and assign on the line here a line weld joint. For example, butt joint with a thickness of 26 millimeters of the cylinder, for example. And we specify also the same here, which stresses we want to check. We say, okay, let's give us the principal force directions, but output finally interacted stress, maybe sigma WED, and compare it again that we have a comparison to 280. Yeah? This you have to detect it from you, this limit stress of weld, of course. And here you can specify if it should use a smoothed or not smooth solution. I would say at the moment for showing you the result we use no smoothing. And now we say we have one line weld, for example here on the top we weld this surface to this surface, and on the bottom the same, so on this line, this surface to this surface. Yeah, now stress strain results will be deleted. You see we have now line welded joints here, and if we recheck it we get member results, surface results and line weld results, where we see deactivate the rest, activate only line welds without mesh. You see now we have only stresses, we have more elements, and ratios only a few, because we defined only for one component a limit stress. Let's check. We have here normal stress. What is maybe the tension between the surface? We have a really huge stress, maybe 70. Bending is almost zero in the middle, what is clear, but only on the end we have some bending because here is the brim. Surface shear is almost zero, longitudinal shear is also almost zero, and the interaction represents the normal stress part in this case. And if we compare it to the limit stress, we get here utilization of 26%, for example. All this stuff, what we have now, members, surfaces, welds, are also in the tables. You have here stresses on members, existing, limit, result, stresses on surface, existing, limit, result, and line welds. But here we selected a few more, so you get no limits and only the existing one, and this final one you check against limit stress. This is sorted by design situation, by loading, by line. So by line we have two elements, so you get two fractures. Yeah. So now I want to open the question, why is this program stress strain analysis, or why is the program stress strain analysis mentions the word strain? At the moment we take care only about stresses, and the answer is it checks also strains. We only have to activate it. So if we open the global program setting and activate the strain analysis, you will see that you get in the surface properties what we just defined only for Mises stress, for example, also a new chapter strains. It's looking similar like the stress table, but it's strains. And we can select here, for example, the Mises strain, also strain vectors in Mises law written. And we have also here a limit plastic strain of 50 promille. What happens if we activate this? Let's run analysis. And we see after calculation that we get no further arm here. So surfaces gets now additionally here a strain result. We see max Mises strain is 0.9 promille of all 4 load cases, of course. The red part is near the brim because it induces bending, of course, also. But what is with this, let's say, limit strain of 50 promille, what is defined? There's no check, and even if I open the table, strains on surfaces, we have only existing strain. Maybe because we have the biggest stress is here 183, it's not reaching the yield stress, so let's inducing or increasing the pressure load to get an effect. I open internal pressure and change it to, 25 bar. And let's run it again. So let's use this stress strain analysis and run it again with a load which reaches the yield strength. Maybe then the program is comparing or checking the plastic strains. But what happens? We have now a stress of which is bigger than the yield strength. The strain is also bigger, 2.3 promille, but we have no check against the plastic strains. Is 50 promille is still not checked, and this is only checked if the program knows what is a plastic strain. So we have to learn the program what is elastic and plastic, and for this you have to go back to the basic input, to the basic objects, to materials, and say, okay, please use for the stainless steel here another material law. It's common, you can use it for every material, and use here isotropic nonlinear elastic. What happens? Now with this setting, the program learns, oh, I have an elastic part and a plastic or nonlinear elastic part. Here's my yield strength. To be comparable, let's use here as yield strength not 330 and 280. And let's see what happens. So if I run now stress strain again, the program recalculates CO1 to 4 because we have now new material properties, so we need new internal forces. They should be detected now linear elastic, of course. And so 2 are already, and the last 2 follows, and now the stress check will be done, stress and strain check. And you see now suddenly we get additionally to the strains, now we get a bigger strain, a plastic strain part of 1.8 and the ratio of maybe 4%. The stress is now not higher than this limit, this yield strength. We defined 280, so at 280 the material begins to yield, and the stress is not going bigger, but we get additional strain, so therefore we have now here bigger final strain, and we get some plastic strains here, especially in the brim. So this was my target, to show you that you can design with this add-on not only stresses, then also strains, and this depends on the material law what you assign. Now, when the program don't know plastic strains, you cannot design it. Now we come to our next point, to the representatives. So we just designed members, surfaces, line welds. So if we go back to our members, you see these 2 racks are almost similar. So if you know the biggest stress, you know exactly that the first have the same design like the another one. But let's pick out one member what is similar. For example, this bottom member. And if we watch here the results, you see the utilization here is 11%, here 7%. But for us means this, I have to control 2 members. So if I say take a look here, stresses on members by member, I have here 2 members. Or if I activate all, I have 18 members. So 18 lines and 18 lines, and have some effect on the documentation later. So to reduce documentation, we invented the system of representatives. You can activate these representatives in the base data. Below settings and options, you have here members and representatives, and after activation you will receive here below basic objects a new arm member representatives, 5 elements. What means this? You get now here such colored bubbles, and if you select one, you see, oh, the arc member both are selected. Here the bottom member both are selected. Here the outer members are selected. So the program finds similarities and catch it up. So for example, for the second, he sees, okay, this member 3 and 12 have the same properties, so I can present it to you as one element. And this means we can use these 5 settings for documenting these 18 members. And we prepared also our stress-strain analysis for this. So if I go here to, let's say, you see, we have now here member representatives. And if we calculate also member representatives, the program designs directly not only members and also member representatives. And to see the difference is now following. If I select now again this bottom member, where we realized we have here 11% utilization and here 7. If we do the same for representatives, you see we have for both the utilization of 11. So the program tries to find similarities and to document it also with this. So it finds the most crucial element or loading for this element and gives us the result for both at the same time. This means finally, when I go to stresses on representatives, I have now, instead of 18 lines, only 5 lines to document the most crucial result. Yeah. And because I just mentioned so often documentation, now let's set up in the last point the documentation. And the documentation is also defined in our program here on the, let's say, bottom point. So we did modeling, we did loading, we did results, and now let's print results in a printout report. For this, I create a new printout report. And you see the same navigator like we have here is mentioned in the printout report. You can document model data, you can document basic objects, type for objects. You can document part lists if you need it. If you don't need it, deactivate it. You can document static results, summary, nodal support forces, whatever. So if you have here this nodal support forces, you have also some more options to specify which data should be documented. This means here at the moment the program shows you all the data how you present it in the main program behind, so in these tables. If you want to have another scheme, you can select this property and deactivate this and say, for example, loading, I want to see this result only for these 4 results, and display in the rows I want to see only values, no extremes and whatever, and in the columns only forces, no bending moments because they are not interesting, for example. This you can do with all elements of the printout report. Further, for the stress check, you see you have here member configuration surface, solid we can deactivate because we have no solids, and line welded. And here you can also document some tables. Let's reduce it a little bit, so no warning and arrows. Stresses on members we don't want. We want to document representatives, and here let's use maybe stresses on member representatives by member representatives. For surfaces we use for stresses surfaces by surface. For line welds by line, for strain on surfaces by surface. And I think this is now everything, and we want to see an overview, for example. Now if we open this document, you will get now a nice styled document for your clients. You see, you get here a template preview with a picture where you can define your client, created by, project name, a content, make it a little bit bigger, some description of geometry, which cross sections you used, which surfaces, which lines, and so on. So all the inputted data is defined here: surfaces, rotated, trimmed, plane, whatever. And finally, you can also jump to results. You see static results. We have this summary and support forces where we defined only locus CO1 to CO4 for forces. So you can have a control on rows and columns in this selector before. And for the stress results, you see also here you get utilizations by representatives, you get utilizations by surfaces, you get results for the line welds, and you get here this strain check. Yeah, and finally the program sums up everything from all add-ons, not only from stress strains and also from steel design and timber in one overview table, and you see here all governing design checks summed up. So, but this is pure table boring stuff, and to give them some life you can print in some pictures, and this is meant that you say, okay, let's document all my designed elements. So for example, the representatives for one rack, so let's view it here in this direction by members without diagrams, and let's print here a numbering of representatives, and you can print this picture now into the report by using here window field and OK. For the surfaces, right, let's say now go back to surfaces. Here we have stresses. We start from stresses. You have here the structure, and maybe you can use here your selection according thicknesses, vaulted head like we started. You can bring in here the maximum and minimum stress by values on surfaces, extremes. And let's print here maybe the stress plot, what is on the yield strength. So we can print this stress here. Okay, then because it's on yield stress, we print also the strains, the final strains. Okay, and the plastic strain ratio. Okay, and for the, let's say, cylinder, it's a little bit different. We have no yield strength, so we go back to stresses, and you see, okay, everything is fine, so we need only stresses and utilization. And here we can also print a picture, and we use here, because it's more complex, a 3D picture. So okay, and sum up this with a stress utilization and go. So you can go ahead like this. You can print much more pictures, but I think for presenting it's fine. What I want to show you now, you have now these pictures inside. You see you have here such different symbols. These red one are 3D pictures. The others are regular pictures, maybe in full scale. So you can spice it up with this picture, but this 3D option is not interesting here in these structures, and more if you export this data into a PDF. So if we export it on PDF, maybe with the letter P, we can create directly a PDF, what is at first looking similar like this data in the main program. But if you scroll down to these pictures what have this 3D option, and if you trust here, you give your client the option not to watch only this data then you can directly look inside. Yeah. So this is a really powerful tool. So you can give your clients more options, more results, and what is I think good for the full project. So now this is the export of the result data from our program into PDF, but we just or a few months ago we invented also here an HTML export. What is here to create the HTML from the report? We can make also here the letter P now, and producing a full package to create the protocol like a website. So you have now here the Google Chrome browser where you see the data a little different like in the main program, because we have only the properties of an HTML, but you get all data written down with pictures and so on. And if we check this on our desktop, we get here a folder, desktop, where we have here a folder P where the program stores all data, so all pictures and result data. So this HTML is connected to this folder. And the interesting fact is now not that you can create a website from your reports and that you can use this stuff in Word or in Excel, because they can also read in HTML data. So you can here read the data here from where is it, desktop P, open, and you get this data also in Excel or Word, and with all links, with all data, and with all figures. So the only case what happens if you read it in directly is that the program cannot notify or change between a point and comma as decimal sign. So for this I only can say please import it with the option advanced here and say decimal sign is a point. And with using this setting you can open this P document again and you will receive here all figures like expected. You get it directly in a table for further usage. You can copy Ctrl-C, Ctrl-U and take it for your tasks. And this brings me now to the end, and I give back to Andreas.
Okay, thank you, Andreas, for this nice presentation. We are a little bit over the time, but I would like to show the website where you can find the recording and the provided model. Just a moment, I hand over the screen. So that's our website. I hope you can see it. Dlubal.com, and then under news and events you can find our webinars. We record all our webinars. Those are the next webinars. That's the webinar of the next week, new features in RFEM 6 presented by me. Then that's today's webinar. If I click on it, and in the next days you will get an email with a link directly to that page here, and you will find the recording in the middle. And if you scroll down, you will find, or you can already find, the model that we presented today here. If you don't already use RFEM 6, then you can download our free trial version, both free full trial version. For example, RFEM 6, and you can download it and use it for 90 days with all add-ons. Also with the provided or showed add-on today. And also other add-ons are included. Just try it. Okay, that brings me to the end. Maybe a last hint when you leave the webinar, where is a small survey. It takes you only 1 minute. You can score us. The worst score is 1, the best score is 5. You can enter a wish for future webinars or what we can improve or something like that. You can also leave it empty or enter a minus or what you want. Okay, thanks again for your attention. Thanks to Andreas for this nice presentation. Thanks to Frank for answering the question together with me. Yeah, and bye-bye.